All right, in this video, we're going to look at question number 2 that says, suppose a thin rectangular plate has a mass density rho, that's a Greek letter there, measured in grams per square centimeter at the point xy. And this density function rho is equal to y times the cosine of xy, where our point xy can vary through this rectangular region R. And this notation here is saying that the rectangular region here is determined by these bounds on x and y respectively. So x varies from 0 to pi over 2 and y varies from 0 to 1, as you can see up here in this figure. Okay, now part A says find the total mass of the plate m, which is equal to the double integral of our density function over this region R. Include units in your answer. Okay, so I guess first I want to just clarify, why is this double integral of our density going to give us the total mass of the plate? Well, if I think about partitioning our rectangular region, and I look at, say, this little differential rectangle right here, okay, this product of the density with dA is just going to tell me the mass of this little rectangular differential region. Okay, why? Well, because the density there is just telling me, well, the mass density in units of grams per square centimeter, and then I'm just multiplying that by my little area, right, in square centimeters. So in other words, this product, yeah, is just going to tell me the mass of this little differential rectangle, in this case, in units of grams, okay? So to compute this double integral, we know from Fubini's theorem that we can compute it in terms of either one of the corresponding iterated integrals, say dx dy or the dy dx integral, right? And both will come out to be the same value, but one might be easier to compute than the other. Okay, so I'm going to go ahead and first write down the dy dx integral. So here is our integral, and for the bounds, well, y is the inside variable, so we'll put its bounds first, and that's from 0 to 1. X being the outside variable of integration, we'll put its bounds from 0 to pi over 2. And now if you look at this integral, keeping in mind that x is held constant, well, I have a y times the cosine of some constant times y. And if you recall from Calc 2, that would require integration by parts, which, you know, it's not impossible, but if we could avoid it, that would be nice, okay? So what I'm going to do is essentially skip over this one, say, oh, well, that's maybe a little bit too hard. Let's consider the other order. So the integral from 0 to 1, and then the integral from 0 to pi over 2 of y times the cosine of xy dx dy. Okay, and now y is held constant for the x integral, and so now I'm just integrating the cosine of some constant times x. Okay, and that's very, very computable. So if I have the integral of cosine of some constant times x, then, well, if I differentiate, say, a cosine or a sine of ax, I'm going to pick up a factor of a. Now, that means when I integrate, I'm going to have to divide by a to counteract that. So I'm going to get 1 over a times the sine of ax in this case. Okay, so let's go ahead and do that here. So I'll get the integral from 0 to 1 of, now I have my y, and that's just treated as constant, times, so now integrating this cosine, well, the y is the constant multiplying x. So as we set up here, I'm going to get 1 over that constant, so 1 over y, times the sine of xy. And then I'm going to evaluate that from 0 to pi over 2. And then I still have my dy here. Okay. And now those y's wonderfully, right, cancel out. That's great. And now I'm going to go ahead and plug in pi over 2 for x and 0 for x. So that's going to give us what? Well, I'll get the sine of pi over 2 times y. And notice when I plug 0 in, I'm going to get the sign of 0. And that's just 0. So in fact, this is all I get, the sine of pi over 2 times y. And now, all right, I can go ahead and integrate that. The integral of sine is negative cosine. And again, if I were to differentiate, I'd pick up a factor of pi over 2. So I'm going to have to divide by that. So I get minus 2 over pi times the cosine of pi over 2y. Now we're evaluating this from 0 to 1. So now if I plug in 1, I'm going to get the cosine of, I'll leave this minus 2 over pi out front, but I'll get the cosine of pi over 2, which is 0. And then if I plug in 1, I'm going to get the, if I plug in 0, I'm going to get the cosine of 0, and that's 1. And so I'll get this minus 1 here. So here I see that my answer would be 2 over pi. Okay, and then again, in terms of the units, well, the rho times dA, right, this product has units of grams, and the integral is just summing up a bunch of these little masses as I arrange throughout my region. So this would have units of grams here. All right, so that would be my answer to part A. And then for B, this is asking us to find the average density of our plate. We call that rho bar. And as we saw in the last video, we just take that double integral and divide it by the area of our region, which in this case is just a rectangle, right? So over here, I'm going to go ahead and say this is going to be 1 over the area of this rectangle, which would just be pi over 2 times 1, so just be pi over 2. And then I'm going to multiply that by the value of my double integral, which I just computed over here, which is 2 over pi. And so then that's going to give us 4 over pi squared. And then as far as the units are concerned, well, we know that the area here would have units of centimeters squared. And the double integral, as we just said over here, has units of grams. So this thing would then have units of grams per square centimeter. And if you give that some thought, that actually makes a lot of sense, because we know that the density function rho has units of grams per square centimeter. So its average would have those same units. All right, that's going to do it for this video. See you in the next.